Okay, I'll welcome to the third week of the live tutorial session, and today we'll discuss some problems on sequences, dense sets, and some from related to Cantor set and contraction mapping theorem mainly. So, which is mainly topic of the assignment problem, like assignment 4 problems related to. So we'll start with this problem first. So suppose X tau is cofinite topological space with the set X is infinite. Then so that for every X belongs to X, the intersection of all neighborhoods of X is precisely equal to the singleton X. So like if you just follow the definition, it is not much hard to see, but can someone help me with that? How do you proceed, or what should be the argument?
If there is some other element in the intersection other than X, then if I'll call that element Y, then I can show that X minus Y is an open set containing X. So it will be a part of the intersection, and therefore this Y cannot belong to the intersection. So there will be no element other than X.
Yes, exactly. So that's the exactly idea, because it is cofinite, so complement of any finite set is an open set, and if I take a particular y that is not equal to x, then complement of y will be a open set like neighborhood of x, and that is clearly not contain y. So so first, clearly that as every neighborhood of x contains x, so this singleton x is clearly contained in the intersection of all neighborhoods of let's say u, such that let's say intersection of all neighborhood a, such that okay, x belongs to a and a is open. That's the like definition of neighborhood. So clearly as each x belongs to a, so this is contained clearly. Now if the intersection a, if y belongs to intersection of all this a, such that x belongs open with y not equal to x, then y complement, which is by definition x minus this thing, is open and x belongs to y complement. Okay, but y does not belongs to y complement. That is, y does not belongs to the intersection also. So which is a contradiction. This intersection a all open, this is exactly equal to x. Okay, this is like very easy to see, so hope there is no problem with it. So next let's go to the next problem. So here like need to describe the convergent sequences and dense subsets in R under like R with the cofinite topology and in co-countable topology. So again this thing, so So R with co-finite topology, what will be a convergent sequence look like? So any guesses in this case, or any particular type of sequence which do converge in cofinite topology? So let's start with, suppose xn. So just start with any convergent sequence, then let's see what can we say about that. So let xn be a convergent sequence in R with cofinite topology. Okay, so it should converge to some point, let's say okay, also suppose this xn converges to some L. Okay, then by definition of this convergent, I should have, if I take any neighborhood of L in this topology, then except from finitely many terms, all terms should lie in that open neighborhood, right? So but okay, just let's, this implies for any open U, let's say, containing L, there exists a natural number such that all the terms, this xn all belongs to U for n greater equals k, right? So this, but what does that mean? That means that if you like accept, but U is an open set in this topology, so U complement is a finite set, right? So in particular, let's take suppose pick any y not equal to L. So for any, let's say, y not equal to L belongs to R. Okay, and consider this open set. The same thing as before. So if I consider the y complement, that is an open set, and here clearly as y not equal to L, so L belongs here. So that means, and thus there exists again a, let's say, ky particular to this y belongs to n, such that xn belongs to this y complement for n greater equal to ky. So in particular, it is saying that xn not equal to y for a like after a finite number of elements. So none of the xn is equal to y. So that is xn not equal to y for n greater equal to ky, right? So for any y that is not equal to L, right? So we cannot have any, so in particular this is showing that this xn sequence cannot have infinitely many repeating terms, right? If I had, suppose, except this L, if I suppose anything x, let's say x is an real number which occurs many times in the sequence. So like for example, if I take xn equal to some let's say 2 for n even, and for n odd let's take it is 3, then this sequence clearly does not converge, right? because if I take like any for example, if I take 2, so it is repeating more 2 3 2 3 2 3 and so on, right? So here it cannot converge to neither 2 or 3, because the complement of 2 will give me like there does not exist any n after which this 2 is not equal to this xn. So similarly 3 and every other point anyway, they are not anyway in this sequence. So those will not be anyway in a limit point, like limiting point, or that mean that this cannot be convergent. So but it can happen that this xn has infinitely many repeating terms, and that repeating terms is exactly equals to L. Okay, so that can very much possible to happen. So this implies that this xn sequence, the sequence xn can have at most one term that occurs infinitely many times. Okay, so this is like one part, that if you have convergent sequence, then we must have the terms of xn can like one term can occur infinitely, or at most one term can occur infinitely many times, and that infinitely many occurring term will be the limit. So we seek the converse of this also, so that we can classify the all convergent sequence there. So we again have to address that if we have like this condition, that if a sequence has at most one term that occurs infinitely many times, then whether the sequence converges or not, then we clearly characterize the all convergent sequences in cofinite topology, that a sequence xn is convergent in cofinite topology in R if and only if that at most one term of the sequence occurs infinitely many times. Okay, so conversely, let's say let xn be a sequence that has at most one term that occurs infinitely many times. Okay, so in this case we need to prove that the sequence will be convergent. So first case, suppose, so case 1, so xn has no term that occurs infinitely many times. Okay, so in this case what will be the like limit of the xn? So goal is to show first of all that this xn will be convergent, and what will be the limit. So in this case I'm saying that the sequence will converge to any point on R. So then for any, let's say x belongs to R, so x belongs to R, and A, and okay, A, B, and any neighborhood, let's say any open neighborhood say there exists some Ka belongs to n, obviously, such that xn belongs to A for all n greater equal to Ka, because if it does not belongs to, there does not exist these many, then we have that there exists some term which occurs infinitely many times, because if okay, so as A complement is finite and this thing xn equal to this the terms of this thing is like an infinite set, right? So all those terms cannot be lie in this A complement, so there must exist some n after which there does not exist anything outside of this an, because these finitely many terms can occur in xn finitely many times. So after those finitely many steps, all the xn surely will lies in A, right? So n is finite and all of the elements of A complement can appear finitely many times. Times in xn by the given condition itself. So I have finitely many terms and like in outside of A, and each of those terms can appear in the sequence xn finitely many times. So finite of finite thing, so we have finitely many terms. So after those many terms, we must have all the xn lies in A, right? So this is clear, right? So this saying that this implies that this xn converges to x for any x belongs to R, right? Converges to x for any x belongs to R. So in particular, if I take like 1, 2, 3, 4 up to n, this thing is all like, so this sequence xn equal to n for, so e.g. that xn equal for n belongs to n. This is a sequence in R, and this xn converges to any real number. Okay, so this is like one thing. So you have a like example of sequence and topological space where like the limit of the sequence is not unique. So in particular, there are infinitely many uncountable number of limit. Okay, so case 2 is that there is exactly one term that occurs infinitely many times. Okay, so xn has exactly one term that appears infinite times. Okay, so in this case, we clearly guess that if one term that appears infinitely many times, then that term, that particular term should be the limit. So suppose LB, let's say L is the repeating term in the sequence. Then for any open neighborhood A of L, so there exist, we should get that there exist. Okay, so first of all, like as previously, this is the repeating term in Xn, and all the except anything that not equal to L, so open, that will be the complement of that will be a neighborhood of this L, and all the terms except finitely many terms, all those terms should be belongs to that neighborhood. So which implies that except this L, no other elements of R can equals this Xn, right? So okay, so in particular I have to choose it, that thing. So A equal to let's say particular this Y complement belongs to L for Y not equal to L. This there exists ky such that Xn belongs to A for n greater equal to ky, that is Xn not equal to Y for n greater equal to ky, right? So this implies that except like any this Xn don't have any other point that repeating, right? So that's also from the clear from this thing. So we claim that this Xn is like the tail of the Xn after a finitely many terms. This Xn is eventually constant. So all the terms after a finitely many terms, all the terms of this Xn is exactly equal to L. Because if it is some like something is not equal to L, then we clearly have a contradiction in this case, right? Because this saying that Xn not equal to L in this case, and there is no other repeating term, so it has exactly one repeating term. So this implies that this Xn equals L for okay. So yeah, so I have yeah, in this case I should not have this because okay, where is the thing? Yes, yeah, so this is follows from as Xn has exactly one repeating term. Repeating term, right? So in particular, as we have seen, the like for singleton set we have considered, and that in that thing it is happening. So in other cases, so in general also, because any other open set will be again like union of these things, and in this case, so maybe I should write that also. So thus for any ONBDA of L, there exists K, because in that case the A complement will be finite, and for each such finite the complement of that like A complement is a finite set, and for each those y1 y2 yn we get ky1 ky2 kyn say, and then take the maximum that thing that will do in this house in our case. So A, there exists so L, this A complement equal to, let's say, y1 y2 yn say, and we have this kyi belongs to n, I equal to 1 to n, such that xm belongs to yi complement. So for m getter equal to kyi, so this implies xm belongs to the intersection of all those yi, I equal to 1 to n complement. So for m getter equal to maximum of I equal to 1 to dot n of kyi. So for this thing, and but this is what this is exactly so this is union of this thing, union of this yi, so that is just a, right? So this implies xn converges to L, hence combining first the initial thing and these two case all together, so recall what we proved. Initially we started with the convergent sequence, and then from there we proved that any convergent sequence can have at most one term that occurs infinitely many times, and then we also showed that if we have a sequence with which has at most one term which appears infinitely many times, then the sequence also convergent. So hence combining both parts, conclude xn in R with cofinite topology convergent if and only if there is at most one term that appears many times, right? So so that classifies the all convergent sequence in cofinite topology. So is there any confusion with this? Yeah.
I still don't understand why a sequence which has all distinct terms, that's not convergent in R, the cofinite topology.
No, with all distinct term, that is converges to any point, right? That's what we showed here just in case 1. So here
So is this a like?
Yeah.
So if it converges to every point, then it's a problem.
No, it's not a problem. So that's why.
But now you have written.
Yeah. I've written that this is in cofinite topology is convergent if and only if there is at most one term in Xn that appears infinitely many times. So in that case, no term occurs infinitely many times.
Okay. Sorry. Okay.
Yeah.
At most.
Yeah. So that all. So in that case, in the case 1, we have no terms occurs infinitely many times. So in that case, anyway, it is converges to any point. And in the second case, it is saying that the term which appears infinitely many times, the sequence will converge to that. That's all. Okay. So next we then have to again classify the dense subset of R in that topology. So okay. So second part. So dense subset dense subsets. Okay, so dense subset means what? So a subset of this R is dense if this A closure, this is whole R, right? But A closure is what? So A closure is nothing but the intersection of all closed set. So this is another definition of the closure, so I'm using that thing. So it is intersection of all the closed set in R that contains A, right? A subset of B closed, right? So here B closed means A, like B complement should be open. So in that case, B closed means like B should be finite, right? So it is like all the finite set and like that finite set that contains A. So if A is suppose let's say infinite, then the only set that can contain this infinite set, so the only closed set that can contain is the whole set R itself, right? Because all other except the R whole set is both open and closed. So in the except that closed set, all other set cannot contain because A is infinite, right? So we claim that any infinite set is dense. So that's almost immediate from this thing. So let A be an infinite set R, then A closure equals intersection of all by definition of closure. So A content in B closed, but I'm using the definition, so B I'm closed means any finite set will be closed. So B is finite. as okay, and this B as B closed if and only B is finite, right, in this topology. So but this is A is an infinite set and B is a finite set. Okay, B is finite, or I should write B equal to R. Yeah, that should also include it. So this finite or B equal to whole of R. So this is clearly must equal to, no set can contain A except this R. So this is clearly R. So clearly any infinite set is dense. Also converse also true, because if we have is dense, and also conversely. So if A is dense, then A must be infinite. Otherwise A will be closed, right? Infinite. Otherwise A is finite, that means it is closed, implies A is closed, and closed means A closer, this is A itself, and it is a finite set. So and as A is finite, so it cannot be equal to X, because X this R. So and A not equal to R, that is A closer not equal to X, so which is a contradiction. Okay, so we must have any infinite set is dense, and also any dense is has to be have infinite, right? So that's classified all dense set in the cofinite thing also. So is this clear? So a set in R with cofinite topology is dense if and only if it is infinite. It is clear, right? Or have any confusion?
No, sir.
Okay, fine. So then we next do the same thing for co-countable. So we have cofinite, now co-countable for the co-countable thing. So in this case the thing is little bit easier. So in this case again start with convergent sequence. So let's say let xn converges to L, okay, and consider A as all the terms xn such that xn not equals L, okay. Then clearly A is a countable set, right? Because the elements of it is like a subset of the elements of this, all the elements of this sequence xn. So xn, this is any countable set, so this A is countable, which is countable subset of a countable set. So this is countable, and this implies that A complement is open, right? And as it is A complement is open, and also as none of the xn is equal to L, so L does not belongs to A complement. That means A is A complement is a neighborhood of. This implies A complement is an when open neighborhood of L. So this implies that there exists K belongs to N such that xn belongs to a complement for n greater equal to k. So except for finitely many terms, all belongs to a complement, but the a complement are that exactly the terms, or like the complement of the terms xn which exclude l. So all of the terms, so this is possible if and only if that is xn equals l for n greater equal to k, right? That's the only possible case, because otherwise all the like a complement does not contain any element of this xn other than l, right? So we must have that this xn equals l for n equal to n. That is, the sequence xn is eventually constant. So eventually constant means after a finitely many terms it is constant. So the converse is also clearly true. Conversely, if xn is eventually constant, that is xn equal to some l for all n greater equal to k, then for any open neighborhood a of l, this so basically a of l, this xn belongs to a for n greater equal to k itself, right? Because after this k all the terms are l itself, and clearly a is a neighborhood of l, so l belongs to a. So this implies xn converges to l, right? Hence xn is convergent if and only if xn is eventually constant. Okay, so this is clear, right? Okay, so then let's again classify the dense set in this topology also. So again the same idea. So here as we classified the dense set here, so the same idea here. So maybe just there we take it as like infinite set and like finite and infinite set. So in this case we should consider like countable and uncountable set, right? So the same way, so any uncountable set will be dense. So claim a subset of R is dense if and only if A is uncountable. Okay, so proof is like the forward part. So A is dense, so this implies a closure which is by definition intersection of all B closed B. So this is same as again intersection of all B equal to either whole of R or B is countable, right? So then and this is equal to all of R. So if A is countable, then A closure equal to A itself, right? As A is closed. Because any countable set will be closed in this co-countable topology, right? So A closure equal to A. So and A is countable, A cannot be equal to R itself. Which is like contradiction. So this implies A is uncountable. The same, like exactly the same thing as before. So conversely, if A is uncountable, then this will imply that the only closed set that can contain A is R itself. This implies A closure equal to R, that is A is dense. So this establishes the claim, right? Hope all the things are clear, right? So we have done classifies the convergent sequence and dense subset in both the topology, cofinite and co-countable topology in R, right? Okay, so then let's go to the next problem. Okay, so here again something related to the interior and closure of the thing. So first one, can someone help me with that? It just easily follows almost from the definition, but this is somewhat useful and saying saying something about the dense set and no height denseness. So how to prove first one? Like proving this is same as proving like A interior complement is A complement closure. So how the interior and closure get transferred under the complement. So that's about that says this problem. So we have to show the both inclusion, right? So let's take this X belongs to. So I'm assuming all this is non-empty. So like if interior is empty, like A is interior, then A complement is anyway okay. So I'm anyway considering this is not equal to phi. So I'm taking some X belongs to this A interior, and this is possible if and only if there exists some open neighborhood u of x such that u is totally contained in A, right? That's the definition of interior point. So, and this happens if and only if this so u is totally contained in A, so u does not intersect A complement, right? So u intersection A complement, this is equal to totally phi, right? It is totally contained in A, so it cannot intersect the A complement, and this means that we get a neighborhood of x which does not intersect A complement. So we must have that x cannot be an closure point of A complement, so it does not belongs to A complement closure. So, and this is if and only if x belongs to A complement closure whole complement, right? So this says that whenever you have this, you get this one, this, so thus A interior is equal to A complement closure whole complement. That is also says that A interior complement is A complement closure. Okay. Second one, similarly, let's say x belongs to A closure, then this means u intersect A for all open neighborhood BDA of open neighborhood u of x, right? So this is not equal to phi, this is not equal to phi for all open neighborhood u of x. So if u intersect all neighborhood of u intersect A, so this clearly happens if and only if u cannot contain in A complement for any open neighborhood u of x, right? So there does not exist any neighborhood that is wholly contained in A complement. So this is saying that x cannot be an interior point of this A complement. So x does not belongs to the interior of A complement. That is, x belongs to A complement interior whole complement, and thus we have A closure is exactly equal to, because if x belongs to here, then I'm saying x is also belongs here, and converse also true that if x belongs to here, the opposite implication will imply that x belongs to A closure. So combining both, we have this. Complement, that means again the A closure complement is A complement interior. Okay, so that exactly saying the interior and closure business under the complement thing. So that we'll use to prove the second one. So what is this boundary of boundary A? So by definition of boundary A, so we'll use both the definition of boundary. So one definition is boundary of A is closure of boundary A minus interior of boundary A, right? But this boundary of A is also defined also is equal to, and this is also equal to A closure intersection with A complement closure, right? So A closure and A complement closure both are closed set, so intersection of being two closed set, it is again closed. So it is closed means this A boundary A closure is boundary A itself. So boundary of, okay, so I have, so this boundary of boundary, this is not exactly boundary, so boundary of boundary A is boundary A closure minus boundary A interior, right? And this is closed, so boundary of boundary A, this is equal to boundary A minus boundary A interior, as boundary A is closed, so closed, that is right. So we need to find, like, to claim that this boundary of boundary A is exactly boundary A, so we must have to show that this boundary A, interior of the boundary A, is empty, right? So now this boundary A interior, so this is again boundary A, we'll use this definition, so this means boundary A intersection, okay, sorry, closure A intersection A complement closure whole interior. But again, it is true for interior that intersection of the intersection of two set is individual intersection of the individual interior. So this is A closure interior intersection A complement closure intersection. Now we just have proved that A complement closure, this thing A complement closure is A interior complement, right? So this is same as this thing intersection with, yes.
Can I use the definition of boundary itself to say that the interior is empty?
Yeah, how do you say that?
Because if an element is in the boundary, it cannot be its neighbor. Any of its neighborhood will not be contained in that boundary set.
Yeah, so how do you like say that from the definition?
Because if I'll take a neighborhood of A,
Yes.
then it will intersect with both A and A complement. Okay. No, I cannot say that from the definition of boundary.
Yes, so that's why there is
Because boundary of A closure minus A interior. Okay.
yes, yeah, so that's why, like, proceed with this thing. And anyway, so this assumption is also there that A is either open or closed, so that might help to that thing, but just I just want to connect this thing with this, that's why I just doing in this way. So like, just using the previous thing, I'm also can say that A complement closure is A interior complement, so A complement and then whole interior, right? So okay, now what happens here? So you have two interior of the set, so if A is closed, then if A is closed, then A closure is A itself, so it is A interior intersection with A interior complement whole interior. But anyway, that thing is like this interior of this any set is already contained in that set itself, so in particular this thing is a subset of A interior complement, so this thing is contained in the complement, and this is I'm taking in A interior, so this is clearly phi. So what happens if A is open? if A is open, then I know the interior of A is A itself. So in that case it is A closure interior intersection with A complement interior, right? Because in that case A interior is A itself. So can you say this is empty? So what happens? This A complement interior, this is clearly contained in A complement, and A closure interior, this is contained in A closure. Yes, and A complement is closed. Okay, so how do I say that this is empty? So in the first case it is clear, because this thing is totally contained in the interior and I'm taking in the intersection, so this is
it's empty because A complement is closed, so it already contains all its limit points. So when I'll take intersection of A complement with A closure, that intersection will be empty.
Okay, I can go one step further also, like this A complement interior of the A complement A complement interior is A closure complement, right? This is also A closure complement. So okay, maybe let's write one step more, then that will be more clear. So again from the previous thing, so this is phi if A closed, and in this case anyway this is A complement, so this thing is A closure interior intersection with A closure complement. So this thing is contained in A closure interior, is contained in A closure, and this is A closure complement, so this is clearly empty. So this is totally phi for A is open or closed. So thus boundary of boundary A is boundary A. Fine. So we used here once the first part using 1, and here also by 1, right? So we have this equality. Okay, so now let's go to the next one. Okay, so we need to check that whether the following points lie in the Cantor set or not. Okay, so like you have seen this Cantor set in the lecture, so can you at least immediately say that why does this 1/3 belongs to the Cantor set of 0, 1?
Because I can write this ternary representation of 1/3, and that representation will only involve 0 and Cantor set when I write a number in the powers of 3.
No, but that representation is work when you're so you are probably using this thing, right, in this AK by 3 power K.
Yes.
Like k equal to 1 to infinity, anything. But in this case,
Yes.
ak belongs to 0 or 2, right? Then we say that
Sorry,
this.
0.
But in
Yes,
this
when
case,
I write 1,
yeah,
the representation.
yeah. But in this case, how do you write this 1/3 as in this form?
I think that was some other number. No, not 1 by 3.
Yeah, for 1 by 3, can you say like, does it belongs or not?
1. It's there 1 by 3 because it is in the first, like when we remove the open interval 1 by 3 to 2 by 3. So 1 by 3 becomes the boundary point of the interval. And
Yes.
boundary point, they always remain in Cantor set.
Yes, that's the property you need here. So, and we know basically this thing one, and also that AB, this belongs to Cantor set of AB always, and so in 0 1 we have that, and like 0 1/3, this this is a subset of okay, this I should not say just as a subset, but okay. So, and so if at the I step we get like deleting this 1/3 part of from this 0 1, each time we get union of like intervals, right? So if AB is one such intervals after this n step, then Cantor set of that particular interval is again contained in the Cantor set of this thing. So, and basically 0 1 over 3 and Cantor set of this thing is clearly contained in 0 1, because this 0 1 by 3 is already obtained in the first, like in the first place. In I1 is 0 1, in I2 you have two intervals, one is 0 to 1/3, another 2/3 to 1, right? So this is clearly subset of this thing. So we have 1/3 belongs here, so it belongs here. So thus 1/3 belongs to C01. So then 3/4, how do you like see whether this belongs or not? Yes, any idea? Yeah, hello, Krishna, do you have anything to say?
Yes, sir. It was about the one example of the sequence that we discussed earlier.
Yeah. Can you say it a bit louder?
Yeah. Suppose we have one sequence in cofinite topology.
Yes.
For even index, if the terms of the sequence are all 0, and
Yes.
for any odd index, if the terms are 1 plus 1 by n, then in the cofinite topology,
Yes.
what would be the limit of this? Because there is only one term 0, which will be repeated infinitely often.
Yes. Then that will be convergent, right?
Yeah, but there was I think you made one point during the lecture that the sequence has to be eventually constant or something, so I got confused.
No, that is eventually constant in the so yes, this thing is like it has to be eventually constant, that thing. Yeah. So suppose you have exactly one term that appears infinitely many times, and other terms is like do not like no other terms does not appear in like more than like it they appears some finite times. Then I'm saying that if you take any neighborhood of that point, let's say in your case the neighborhood of 0, so any neighborhood of 0, the complement of that neighborhood is finite, right? So except those so look at those finite points. So finite points okay, in this case I am say this is eventually constant. right, that is
That was
separate.
in co-countable, I think.
Yeah, co-countable
Eventually
case. That thing is
Yeah, but
eventually in this case you have still the convergence thing you have, because the complement is a finite set, and like the finite set, those elements can appear in the sequence finitely many times. So you just delete those terms. After those terms, the all the terms surely will lies in your neighborhood of L. That's the argument.
so if
Yeah.
so the example that I took up,
Yeah.
the 0 happening occurring infinitely many times,
Yes.
and 1 plus 1 by n occurring for each odd index.
Yes.
In the co-finite topology, can
Yes.
we just analyze a little bit?
Yeah. Okay.
I mean,
Sure.
like at the not.
Yeah.
that.
Sure. Can do that.
Thank you.
Okay. So your sequence xn is 0 for n even, and 1 plus 1 by, let's say, n for n odd. So take let A be any open neighborhood of 0 in R. Then A complement is finite. A complement, so 0 does not belongs to A complement, and A complement is some finite set, let's say y1 through yk. Okay, now by our like this thing, so then y1 through yk can appear like all those in the odd term. So clearly this y1 through yk are not equals 0, right? So if they are equal to some 1 plus 1 by n, so they can appear at most 1, right? Then they can appear in xn at most one time. So take whatever the numbers, so let's say all of them appear like y1 through yk, all of them appear in xn. So if it is does not appear, it fine. If they appear, so suppose they appear some n1 into nk, so at most one time. So suppose yi equal to x ni for ni belongs to like n, or there does not exist any ni. So that's the thing. Okay, so how do I write that thing? Maybe okay, suppose for ni and this I equal to some how do I say, p1 through pl, and this p this belongs to 1 through k. Okay, so suppose l many of them appears, and they are exactly the like nth term of this sequence, right? This is clear. Is this clear?
Yeah, it's clear.
Yeah, so then take k m to be maximum of this thing, so max of those n1 through n NLES or NPL, yeah, NPL, or maybe NPI, right? yes, NP on through NPL, because I is my P1 through PL. So yeah, so max of this thing, then none of this thing like this A set, so then xn is belongs to A for all n greater equal to m, because none of the terms, so all of the like except these many terms, all terms are there in A. So only this term can appear in the sequence, but those are those I have already removed, because after this maximum of this thing m, this thing in xn they does not appear, right? So clearly xn cannot be equal to any of this y1 through yk, or maybe I should another. So then xn not equal to yi for and I equal to 1 to k. So this implies xn belongs to A for all n greater equal to m. So this implies xn converges to 0, because this is true for any neighborhood 0 of R. So yeah. So any other, yeah.
Yeah, there was one small doubt. Can you just pull it up the slide from co-finite topology, the proof where you supplied to us?
Co-finite topology, in which case, like convergent sequences, or
Yeah, the starting of the proof of that question.
oh, okay, yeah,
no, yeah, this page.
yeah,
In the second line, you wrote that suppose xn converges to L.
yes,
Right.
So
Without knowing beforehand what kind of topology there is it safe to really, think of only one limit of this sequence?
No,
there could be multiple.
Yeah, there can be multiple limits. So I'm only saying, so once I say that xn is convergent, so there is some limit. I'm not saying this L is unique. So I'm just supposing that xn belongs converges to L. L may be different also.
So L is a candidate for any of thing that it might converge to.
Yes. So I'm not just so convergent means it converges to some point. The converging point may not be unique, but we have some limit. So that limit I'm just assuming to be L.
Thank you.
Yeah. Okay. So any other questions later part, or?
So far so good. I don't have any other question.
Okay, good. Then okay, where we are? So we are in this Cantor setting. So in this set we are seeing that which points of these three, maybe just I pick arbitrary these three. So which of these lies in the Cantor set of 0, 1. So first one, we just have seen that the boundary point of like if I consider AB and the Cantor set of AB, then the boundary points always lies there. So in particular in our case, if I just in the first case this complement this 1/3 open 1/3 to 2/3. So just deleting that from the 0, 1, we see that close 0 1/3. This is a subset of this Cantor set of 0, 1, and 1/3 belongs here. So it belongs also Cantor set of 0, 1 also, right? So this thing is done. So for 3/4, like how do you proceed to check whether this belongs to the Cantor set or not? So any idea? Like, can you use something of this thing? Can you represent 3/4 as like sum of this ak/3 power k, or ak belongs to 0 to or in general, how do you find like such a representation, if it is at all possible to represent? How do you find such a representation for a let's say fraction, less than one fraction? Any idea?
There was one article on Wikipedia regarding how to write the
Yeah, so it is
representation of
it is in general true, like whenever you want to write some numbers, it is just like binary, like binary number. How do you write binary numbers in um, suppose you are given 0.2, how do you write this in the binary? So you do multiply with 2 and still multiplying with 2 unless you get a like integer part in that. Where you get the integer part, you put there 1 and elsewhere it is 0, right? So the same thing, like similar representation, you can do this thing. So this is nothing but saying that you represent this this element in like your in like it is not decimal, so binary, it is I see tertiary representation of the element. So tertiary for 3/4, so 3/4 you just for the tertiary representation, so you multiply by 3, so what you get, so it is 9/4, so it is 1 plus 1/4, right? So it is 1 you get, so in the first place, so the power of like the coefficient for 3 will be 1, so then you start with again 1/4, then go to 1/3, so it is just 0 plus 3/4, so in this case it is 0. Then again you multiply 3/4 with 3, so you get again 1 plus 1/4, so it is 1. So it is the place for like 3 power minus 1, right? It is the place for 3 power minus 2, it is for 3 power minus 3, and so on. So it is just keep repeating, right? So 1 0 1 0 1 0, so it is keep going. So from that thing you can actually write that 3/4 as 1/3 plus 0/3 square plus 1 by, so it is 1 by 3 power minus 3 power 3 plus again 0 by yeah,
something came up. Shouldn't that be 2 instead of 1? I mean, 1 plus 1.
yeah, sure, so sorry, really sorry, yeah, sure, yeah. I just this is surely 2, yeah, 9 by, yes, sure, yes, so right, so yeah, this is will be 2 in those place, so it is 2 0 2 0 and so on, and so on. So clearly this you can write in this form, so it is indeed belongs to like so it is ak by 3 power k belongs to n, and in particular the ak is 2 at or the odd place, in odd, and in even it is 0. So clearly this belongs to the Cantor set 0 1. The same thing you do for this 35 by 36, or maybe it is like the other thing, like how do you eliminate, if you want to eliminate the point from that set, then you show that this belongs to something in between. So you just, if you can see that this 35 by 36, it is belongs to something, let's say 1/3 power k and 2/3 power 2/3 power k, right? Yeah, so in particular, let's say suppose, so if you can find such k, then it clearly does not belongs to the Cantor set, right? That is another process. So somehow you get representing that thing in this tertiary representation, then there you somehow get this coefficient not to be only 0 or 2, you get some 1 somewhere. Then you see whether that this element somehow belongs to in this interval or somewhere, which we delete in the process in the process of constructing this Cantor set. Then you also can say that this does not belongs to that set. So that is another process. So in this case, I think it is true for 2 itself. So let's see. Just a minute. Okay, no, this 35 by 36 is also you can get, this is also lies in the Cantor set. Yeah, so the same, do the representation and you will get that. And 35 by 36 is also written as 2/3 plus 3 square plus again the same thing, like 2 3 cube plus 0 3 4 plus 2 3 5. So this is just the repeating part of this one. So keep going on. So this actually again belongs to 0 1. So the another thing is you take 4/9, then this 4/9 in between 1/3 and 2/3. So clearly this does not belongs to, because we delete this particular interval, right? So 4/9 does not belongs to C01. So that's how basically you can find points which belongs to the Cantor set and which does not belongs to intercept. Okay, so that's maybe helpful in some assignment problem. Okay, so now let's go to this one. So can you construct a nested sequence Cn of closed subset, give some finite diameter or infinite diameter in a complete metric space such that their intersection is phi? So this is basically exactly the so Cantor intersection theorem, the necessary condition for the diameter to go to 0, that part I'm removed, and then I'm saying that is it possible to construct a sequence where the that theorem fails. So the diameter thing is somehow necessary to guarantee this is particularly non-empty and it is a singleton set, right? So because every other, all the other thing is assumed, so it is nested, closed sets, complete matrix space is also there, but the diameter thing I'm saying it can be finite or infinite. If it is finite, then anyway that is violating the thing, but even it is finite, then can you also give some example of this Cn such that this intersection is still empty? So that somehow says that the condition are necessary for the theorem. So any idea, at least in the infinite diameter case? So let us complete matrix space is known one is the R with the usual metric. Yes.
We can take n to infinity. Sets closed and.
Okay. N to infinity. Okay. Sorry. Yes. Sure. I thought you said to the L2. Okay. Yeah. So this is complete metric space. Here you take as suggested. So Cn, let's take n to infinity closed of n. So this is clearly closed, and also nested because it is getting like smaller and like not smaller, I should not say smaller, but each of these are contained in one another. So closed for, and select C1, Cn, content Cn minus 1, content to all of these are content C1. So they are nested, and diameter of Cn is infinity, right? Because there are take any endpoint, and diameter cannot be finite because this is an infinite interval, and the distance is exactly infinite with respect to that. So this is infinite, but what is the intersection of this Cn? So this is claim that this is empty. Otherwise, if there exists some point here, then that should imply that that belongs to all of this Cn, but clearly sees that this is like getting like it is okay. So that is again like something that follows from Archimedean property phi. Otherwise x belongs to this intersection Cn, implies x belongs to Cn for n belongs to n. That means x is greater equal to n by choice of our Cn for all n belongs to n, right? But this is a contradiction because we know for every real number there is a natural number which is greater than that that real number, right? So which is a contradiction to the Archimedean property. Property, so we can't have this is not empty, so it has to be empty. So can you give something finite diameter example? Yeah,
we can take a finite interval, and at the starting endpoint I can write a as a plus 1 by n, and I'll fix the other end.
a plus 1 by n and fix the other end, let's say b. So this is your Cn.
Closed interval, yes.
But does the intersection is empty?
Oh, sorry, I have to take other end.
So obviously this is a like violation of the Cantor intersection. So in particular this intersection, if you see that okay, like this intersection of this Cn, okay, it's depend on the thing, right? So a plus 1 by n, so it is getting
I think it's a minus 1 by 2 to a plus 1 by 2.
a minus 1 by 2 means
A minus 1 by n to a plus 1 by n.
okay. A minus 1 by n to plus 1 by n, yes, sure. So a minus 1 by n to a plus 1 by n, yeah, in that case also. So So it is getting to A, and finally, so okay, this is your, let's say, H point here, and 1 by n. So initially it was A plus 1, but this is okay, this is A minus 1, A plus 1. So it is getting smaller, but anyway, A is always content here, right? And it is indeed like this is this thing. So here indeed you are applying the Cantor intersection, right? Because in this Cn
Yes,
the diameter,
because it's closed bounded and diameter is going
yeah,
to 0.
diameter is going to 0. So that clearly will not give you any counter example. So you have to go something diameter condition. Like you have to take your set so that violates the diameter thing. Okay, so the like a good idea is to just change your metric. Okay, where the like everything is finite. Mainly the distance function is bounded. So every set has finite diameter. So can you give me some metric on R which is with respect to which it is complete and
Metric.
discrete metric? So discrete metric complete on R?
Every
Yeah, you have to
discrete
prove.
metric only constant sequence are Cauchy, and
Yeah.
they are convergent.
Yeah, exactly. So that's obviously a good thing that in discrete metric on any set discrete metric is always complete, because the only like Cauchy sequence are convergent because they are, so let's say xn is Cauchy in discrete. So this will imply that this d of xn xm is less than epsilon. So you particularly choose anything less than 1, let's say half. Then by Cauchy thing you know that for n m both is greater or equal to k, say, but this metric has only two values, 0 or 1. As it is less than half, so it cannot be 1. So this implies that is xn, this like dxn xm is 0 for all nm greater or equal to k. So this implies that this is 0 if and only xn and xm are equal, right? So all the terms after k, they are all same. That means they are eventually constant. So that constant will be the point where this sequence converges, right? So constant. So like all of the constants, so dxx is always 0 there, so that is convergent. This implies that let's say R, let's take R itself, R with discrete is complete and any diameter thing is finite. So the like same example will work anyway. So also the same thing, the diameter, like anything single other than the singleton set all has distinct elements. So dxy is 1, so there it is already 1, so diameter of Cn is constantly 1 for all n. The same example I'm considering, and still you have the intersection is not changing anyway, so that intersection thing is still empty, right? So this is like one example in infinite thing, infinite diameter, and here it is finite. Okay, so then let's go to the next one. So here again another thing that might be helpful in solving some problem in the assignment. So here I'm saying that find a topological space with exactly 64 open sets, but the topology should not come from any metric. So can you think of something topology that comes from metric with exactly this many open sets? So the topological space in your hand, you can choose anything. So can you like think of something which has 64 many open sets?
I can assume I can take a set X in which there are 6 elements.
Yeah.
And then power set of that set will have 2 to the power 6 open sets.
Yes. Right. So
that will be discrete.
Yeah, that will be discrete. So that's why I particularly mentioned that it should not induce from any metric. So can you think now of some low topology which consists of exactly 64 but does not comes from any metric? So the hint is basically, so the fix again the same set as you mentioned. So let's take X to be this X1 through X, let's say 63, okay, some finite set. So in this set, if any topology that comes from metric on a finite set, the only possible metric is discrete metric. Like possible metric should not I say only discrete, but up to some scale it is discrete metric, or like equivalent to discrete metric. That means all the sets should be open set if it is anyway comes from any metric. So the first thing is, then if a topology on X is induced from any metric, so you just verify this thing that, so it is just easy verification that if you have a finite set and you have a metric on that set, so you can individually consider the distance between each of those points. So namely you have 63 choose 2 many choice, so you have those many elements, but anyway that set is a finite set. So you consider all of them, consider the minimum of that thing, take half of that thing and consider the ball around that. So clearly that is consist of only one single point, right? So that is an open set, but that is a ball by definition, so that is an open set. So every singleton set in particular is open, so that means that it is equivalent to discrete thing. Any metric, then every subsets or every subset of X is open. That means the topology should consist of the 2 power 63 many elements, right? So this is first observation. So you construct some topology on X which does not contains that many element. So that will guarantee that the topology does not comes from any metric. So can you have something like trivial something topology which like trivially will satisfies the required condition that anyway it is finite set, so the topology will be subset of the power set of X, so topology surely will be finite. So can you like trivially get some collection of open set where you don't have to bother about the like finite intersection or union? They will trivially satisfied. So can you think of now some topology? Okay, so what about this thing tau? Let's consider this thing. So singleton x1. Okay, so I should start with the empty set, because empty set and the set always contain in the topology. So now I will consider like set such that they are already the intersection and union is like one of those sets. So that is again comes from the like you either like take your sets as nested sets, right? So in AB I always you have like, how do I say, so you take your subset so that they are always have either A contained in B or B contained in A. Then the union or intersection always be one of them, so you don't have to add more elements to those. So one particular choice in this case, that's why you can take x1, then keep adding x2, x3, xn with that. So x1, then take x1, x2 and so on up to x1, x2, x62 and then full set x. Okay, so this clearly have 64 elements, right? Because this is 63 element, one is 5, so 64 element, and clearly it is a proper subset of the power set of X, right? So this implies tau is a topological space with 64 open sets, and it is not induced from any metric. The topology thing is already from my choice, it is satisfying the like finite intersection and union, right? Okay, find all dense subset here. So again you just follow the property definition of the closure. So suppose A is okay, so in this particular case, let's say A closure is again by definition intersection of all those B which contains A and B is closed. But what are the closed set here? So closed set are nothing but just like I'm denoting it by tau complement, but don't confuse with this as subset of px minus this thing, but this is like a notation. So this consists of obviously phi complement is x, complement of this thing is x2 through x63 and on the way up to x63, right? So in this case you are actually deleting x1, then x1, x2, then x1, x2, x63 up to, and then finally you have phi. Okay, so the number of closed set is also 64, and if you take anything, so you need to get this intersection. So if it is not x, then it is clearly not will be a closure cannot be x itself. So you have to consider your A like which like where the closed set, only closed set that can contain A is x itself. So from there you can see that these are the all closed set. So if anything that that is not of this singleton x63 or x62 63 on so on, then the only set that can contain the set A is X itself, or closed set that can contain A is X itself. So let's say A is anything. So if A is not subset of the biggest thing in this set, so x2 through x63, then A closure is X clearly, because the only set that can contain A is X itself. The only closed set that can contain A is X itself, so it has to be X. So all other case, if it is a subset of this x2 through x3, then that will be a closed set, right? Am I saying correct? Not all subset, right? Yeah, fine. So any subset that is a subset of that thing, then the closed set that can contain that thing is this set. Yeah. So there that is not exactly equal to X. So it is also, the converse is also true. So a subset of X is dense if and only if A is not a subset of x2 through x63. Okay, is this clear?
Yes, sir.
Okay, so next let's go to the next one. So it is again something related to the assignment problem, like similar thing, but here I changed the polynomial, but I think the idea will be mostly similar. So how if you are given a polynomial and you are asked to prove that there is a unique root in 0 1 using contraction mapping theorem, so how do you proceed for that case? So Banach contraction mapping means you have to produce a contraction map, then you say that is a fixed, unique fixed point in that interval, then you can get that this px at 0. So you have to arrange this px in such a way that the root you can write as a fixed point of some other function. So can you have some idea to represent px in that form?
Yes, sir. So we'll define f of x as x cube plus 3x square plus 1 divided by 7.
Okay, so you are saying this is x cube plus 3x square plus 1 by 7. Then if fx equal to x has a root, that means px equal to 0 has a root. So then px equal to, or the other way may be yes, then fx equal to x has a solution will implies that px equal to 0 has a solution. That means it has a root, but I have to guarantee it be between 0 and 1. So can you prove that this fx is a contraction map? How do you prove that this fx is contraction? Is it really contraction or anything? Any idea? Okay, but see that the, like, in this case this is a polynomial, so the thing that I to me at least the easiest one is, like, you consider a prime x, then it is 3x square plus 4x by 7, and this is for x belongs to 0 1, this is less equal to 1. But if I can if I could have that this is strictly less than 1, like bounded by something strictly less than 1 quantity, then by Lagrange thing I can, like, from the Lagrange mean value theorem I can easily say that this f is contraction. But in this case it is like at the 1 point it is exactly 1, so I can't say from this function. So you have other choice of function, so that this fx equal to x has solution will imply that this px has a px equal to 0 has solution. So let me take this function, I've taken it. Okay, so just take x common from here, so it is x square plus 3x minus 7, just send it on the other side, so that choice will give you surely a contraction map. So take this x square plus 3x minus 7. Okay, then fx equal to x as a solution imply px equal to the same thing, so equal to x will give you px. So then f prime x will be f prime x will be 2x plus 3 by x square plus 3x minus 7 square, and it is less equal to your put the highest value above, so it is 5, and here it is the put the lowest thing, so it is 49. So clearly it is strictly less than 1. This implies f is a contraction. If the derivative is a differentiable function which, like, x belongs to close 0 1, okay, 0 1, so this you just apply Lagrange mean value theorem. Lagrange NPTEL. Okay, so this implies fx equal to, there exists unique, so there exists unique let's say unique alpha belongs to 0 1 such that f alpha equal to alpha, that is by Banach contraction mapping. By Banach contraction mapping, so if alpha equal to alpha, that will imply that this p alpha equal to 0. So that's the, like, required thing in our case. So it has a unique root in between 0 1. So that's easy, just you have to take your function carefully so that you get that as contraction. Okay, so next we have 2 more, and it is just easy. So find a contraction from open 0 close 1 to open 0 close 1 such that it has no fixed point. So it is again a necessary, like, it is showing the Banach contraction mapping thing is not whole in incomplete matrix spaces. So here that closed 0 open 0 closed 1, that is not complete, because 0 like here you can construct a Cauchy sequence which converges to 0, but 0 is not in the space, so that is not convergent. So basically the completeness in the Banach contraction mapping theorem is necessary. That's what saying this problem. So can someone give me any immediate choice of contraction which has no fixed point? Okay, so the EG, like take anything, take any k greater than 1 belongs to n. Okay, and define fx to be x by k for x belongs to open 0 closed 1. Then it is clearly a contraction, because then fx minus fy modulus of this thing is nothing but 1 by k into x minus y modulus. 1 by k is strictly less than 1. If it's contraction, or you don't have to take this edge. Yeah, don't have to take belongs to n. Right, then 1 by k is anyway less than 1. So this is a contraction, but what is the fixed point? But fx equal to x implies that, not, let's say that implies that kx equal to x. This implies x equal to 0, right? Because k is greater than 1, so k minus 1 into x is 0. K minus 1 is non-zero, so x is 0. But this does not belongs to open 0 closed 1, right? So this implies it has no fixed point. So this is that thing that Banach contraction mapping does not hold in complete matrix space. Okay. So I'm using the induced matrix of induced matrix of R in open 0 closed 1. Okay. Next one, the final thing is you show that closed AB in R is a G delta set. So recall the G delta set is what? So I should be able to write these as intersection of countable intersection of open set, right? In general, countable intersection of open set is need not be open, so that's why we indeed say that this is a closed set, but that I write that as intersection of countably many open set. So again, any idea how to write it? Can you write it as, so can you give me some Cn where such that intersection of is open in R and intersection n equal to 1 to infinity, this thing is closed AB. Then we're done that this is a G delta set. But it is easy to this 1 by n thing always there, so you just take a minus 1. Yeah,
I think we can take Cn as from the left and a minus 1 by 1000 and from the right end we can take b plus 1 by 1000 n.
1000 n means
In the denominator, 1 by n, so we can just take 1 by 1000.
Yeah, so depending on, because you have to ultimately, yes, sure, you can take other thing to be just Yeah, so I just wanted to it countable. So for all n, yeah, you can start with just finitely many thing, but finitely many thing will not give you exactly right. You have to take infinite.
Yeah, that will still be infinite, right? If I just
Yeah.
take a minus 1 by 1000 n
Oh,
for any n
okay,
in
okay, okay.
natural term.
1000 and okay, okay. I thought just 1000. Yeah, sorry. Yeah, yeah, sure.
As long as a billion n.
Yeah, 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 yeah. Yeah, the 1 by n will work. So 1000 and it's also you can take. Yeah, sure. So this is an open set in R, but intersection will be just because this thing, a closed interval AB is always contained in Cn, and you can just check that this thing is indeed whole of AB. So this shows that this is a G delta set. Yeah, so that's all I have for today. So do anyone have any other question or anything that we have discussed today?
Will this video be available for any later viewing
Yeah, sure.
on the platform?
Yeah, you have that Excel sheet, right, where the this note and the video link are there. So in the YouTube, this video will be available for sure. But it
Thank
might
you.
take a like you may get this tomorrow sometimes. So it takes time to upload in the YouTube. So that's why. Okay, so this will be available, and the note will be also available. Okay, so if there is no other question, then we'll stop for today and again meet next week. Okay, bye then.